Hello, and welcome to your ultimate guide for the D429 OA, Introduction to AI for Computer Scientists OA course. My goal today is simple: give you everything you need to fully understand the key concepts, master them, and walk into your D429 OA exam with total confidence. In this video, we'll cover AI definitions, intelligent agents, task environments, knowledge representation, probabilistic reasoning. And remember, our website offers free exam guides and practice questions to help you ace your D429 OA exam. You'll find the link in the description below, so be sure to check it out and get the resources you need to study smarter, not harder. So let's dive right in. So what is artificial intelligence? At its core, AI refers to machine-driven systems that demonstrate human-like intelligence and problem-solving abilities. That sounds simple, but there's real depth here. The exam will test whether you understand the difference between a system that follows rigid rules and one that actually reasons through problems the way a person might. Here's where students get tripped up. Intelligence and rationality aren't the same thing. Intelligence means the ability to understand, apply knowledge, and work through complex problems. Rationality is about making sound decisions. An AI can be intelligent, meaning it processes information well, but still make irrational choices if its decision-making framework is flawed. The exam loves to test this distinction. Think of it this way: a chess computer is intelligent because it can analyze millions of positions, but if it's programmed to always sacrifice its queen regardless of the situation, that's irrational. Intelligence is about capability. Rationality is about using that capability to make decisions that actually make sense. Keep those separate in your mind. Now let's talk about the Turing test, which shows up constantly on exams. Alan Turing proposed a simple question. If a human can't tell whether they're talking to a machine or another person, does that machine exhibit intelligence? The standard Turing test focuses entirely on text-based conversation. A judge asks questions and tries to figure out who's human. But here's what makes this interesting. The total Turing test goes further. It adds perception and physical interaction capabilities, so the machine would need to see objects, manipulate them, and respond appropriately. This distinction matters because it acknowledges that real intelligence isn't just about clever conversation. It's about engaging with the physical world too. On your OA, expect questions that ask you to identify which test is being described. If it's purely conversational evaluation, that's the standard Turing test. If they mention vision, touch, or physical manipulation, you're looking at the total Turing test. Don't overthink it. Just look for those physical interaction keywords. What we just covered is exactly the kind of material you'll find in those free practice questions I mentioned. They're designed to test your understanding the same way the real OA does. Not just memorization, but whether you can apply these concepts when questions are worded differently. Let's move to the philosophical foundations of AI. Dualism is the idea that two distinct and independent realities exist. In AI terms, this often refers to the mind-body problem. Is consciousness something separate from physical processes? This philosophical debate shapes how we think about whether machines can truly think or just simulate thinking. Empiricism takes a different approach. It argues that knowledge comes through sensory experiences. You learn about the world by observing it, touching it, experiencing it directly. For AI, this connects to systems that learn from data rather than being programmed with rules. Machine learning is essentially empiricism applied to computers. Then there's induction, which is drawing general conclusions from specific observations. You see 100 white swans, so you conclude all swans are white. AI systems use induction constantly when they find patterns in training data. The risk, of course, is that patterns can be wrong. Maybe the next swan you see is black. Legal positivism might seem out of place in an AI course, but it matters. This is the idea that rules are valid because legitimate authority created them, not because they're inherently moral. For AI governance, this shapes how we think about regulations and who gets to decide what AI can and can't do. I know we're covering lots of detailed information, and you might be wondering how to practice applying all these concepts. That's why I created those free practice questions. They'll help you work through problems that combine multiple concepts exactly like your OA will. Now let's get into types of AI systems, which is heavily tested. Rule-based systems were the earliest form of AI. They work by following predefined if-then rules. If the temperature exceeds 70 degrees, turn on the fan. Simple, predictable, but limited. They can't handle situations the programmer didn't anticipate. Machine learning systems are fundamentally different. They learn from data without explicit programming. Instead of telling the system every rule, you show it thousands of examples and it finds patterns itself. This is why machine learning can solve problems that would be impossible to program manually. Too many variables, too many exceptions. Natural language processing enables AI to understand and generate human language. When you talk to a voice assistant or use translation software, that's NLP at work. The exam might ask you to identify which AI type handles text understanding or speech recognition. NLP is your answer. Computer vision is about interpreting visual information from images and videos. Self-driving cars recognizing stop signs, medical systems detecting tumors in scans, facial recognition unlocking your phone. All computer vision applications. If the question involves images, video, or visual analysis, think computer vision. Hybrid AI systems combine multiple techniques. A self-driving car doesn't just use computer vision. It combines vision, machine learning for decision-making, and rule-based systems for traffic law compliance. Real-world applications rarely use just one approach. They mix whatever works best for the specific problem. If some of these concepts feel challenging right now, that's completely normal. Complex topics take time to sink in. That's exactly why those free practice questions exist. Working through problems repeatedly is how these concepts move from confusing to automatic. Let's shift to intelligent agents, which is a major exam topic. An agent is anything that perceives its environment through sensors and acts upon that environment through actuators. A robot with cameras and wheels, a software program with data inputs and screen outputs, even a human with eyes and hands, all agents. Here's terminology you need cold. A percept is the content of an agent's sensors at a given moment. What the agent sees right now. A percept sequence is the complete history of everything the agent has ever perceived. The distinction matters because some agents only react to current input, while others consider their entire history. The agent function maps percept sequences to actions. Given everything the agent has perceived, what should it do next? This is the core of agent design. You're essentially defining behavior as a function, where inputs are perceptions and outputs are actions. PEAS is an acronym you must memorize. Performance, environment, actuators, sensors. It's a framework for describing any intelligent agent. What defines success? Where does the agent operate? What can it do? What can it perceive? Expect questions asking you to identify PEAS components for specific scenarios. Simple reflex agents are the most basic type. They act based only on current percepts with no memory of the past. If this, then that. A thermostat is a simple reflex agent. Temperature low, turn on heat. Temperature high, turn off. No history, no planning, just immediate response. Software agents are programs that act on behalf of users or other programs. Your email spam filter is a software agent. It perceives incoming messages and acts by sorting them. The key is that it operates autonomously, making decisions without constant human input. Learning agents are more sophisticated. They improve over time through 4 components. The performance element selects actions. The critic evaluates results and decides what modifications are needed. The learning element makes changes to improve future performance. The problem generator suggests exploratory actions to try new approaches. Remember that mastering these concepts takes practice and application. The free practice questions are designed specifically to help you take what you're learning here and turn it into exam-ready skills. Don't just watch this video once, practice actively. Now let's cover task environments, which describe the world an agent operates in. Observability is first. A fully observable environment means the agent can detect all relevant aspects of the current state. Poker with hidden cards is partially observable. A surveillance camera in a dark room might be unobservable, detecting nothing useful. Agent configurations matter for the exam. Single agent means one agent operating alone. Multi-agent means multiple agents interacting. Then there's competitive versus cooperative. Chess is competitive, two agents with opposing goals. A collaborative robot team is cooperative, multiple agents working towards shared goals. Deterministic environments have predictable outcomes, same action, same state, same result every time. Non-deterministic or stochastic environments involve randomness or uncertainty. Rolling dice is stochastic. Moving a chess piece is deterministic. The exam often asks you to classify scenarios by this dimension. Episodic versus sequential is another key distinction. In episodic environments, each action is independent. Today's decision doesn't affect tomorrow's options. Sequential environments are the opposite. Actions have lasting consequences. A chess move affects all future possibilities. Most real-world AI problems are sequential. Static environments don't change while the agent is deciding. Dynamic environments change continuously. Semi-dynamic environments don't change the world state, but might change the agent's score or performance while it deliberates. Time pressure creates semi-dynamic conditions. Discrete environments have finite countable states and actions. Chess has many states, but they're all distinct positions. Continuous environments have infinite possible states. Driving a car involves continuous variables like speed and steering angle. This distinction affects which algorithms work best. Known versus unknown refers to whether the agent understands the environment's rules. A known environment means the agent knows the outcomes of its actions. Unknown means it must learn through experience. This isn't about observability, it's about understanding how the world works. As we wrap up this detailed overview, remember that understanding these concepts is just the first step. The real mastery comes from applying them, which is where those free practice questions become invaluable. They're completely free and designed specifically for OA success. Let's move to knowledge representation and reasoning. Ontology is a method for organizing knowledge by defining concepts and relationships between them. Think of it like building a vocabulary and grammar for a specific domain. Medical ontology defines what symptoms, diseases, and treatments are, and how they relate. Observation sentences are statements about facts in a domain. The patient has a fever. The car is moving at 60 miles per hour. These are building blocks for knowledge bases. The exam might ask you to identify observation sentences versus rules or inferences. Classes and hierarchies organize things into categorical structures. A dog is a mammal is an animal. This hierarchy lets AI systems make inferences. If all mammals have hearts and dogs are mammals, then dogs have hearts. Simple logic, but powerful when scaled. The semantic web extends these ideas to the internet. It enables data sharing through standardized ontologies so different systems can understand each other's data. When your calendar and email automatically coordinate meeting times, they're using shared ontologies to communicate. Semantic networks represent knowledge as graphs with nodes and edges. Nodes are concepts, edges are relationships. It's visual and intuitive. Dog has 4 legs. Dog is a mammal. Draw it out and you can see the structure immediately. The downside is complexity. Large networks become messy and hard to manage. Description logics are formal, structured category definitions, emphasizing tractability and efficient reasoning. They sacrifice some expressiveness for computational efficiency. When you need to actually compute answers from knowledge bases with millions of facts, description logics keep things manageable. Event calculus describes events and changes over time. When did the light turn on? What caused it? What happens if we flip the switch? This matters because the world isn't static. AI needs to reason about sequences and causation, not just snapshots. Fluents are things that can change. Temperature is a fluent. Game score is a fluent. The door being open or closed is a fluent. Event calculus uses fluents to track what's true at different points in time as events occur and cause changes. Modal logic deals with necessity and possibility. Something is necessarily true if it must be true in all possible situations. Something is possibly true if it could be true in at least one situation. This lets AI reason about hypotheticals and alternatives. Linear temporal logic reasons about sequences over time. First this happens, then that happens. Eventually something else happens. It's used heavily in AI planning and verification. When you need to guarantee that a system will eventually reach a goal or never enter a dangerous state, temporal logic is the tool. Propositional attitudes describe how agents relate to mental objects like beliefs and desires. Knowing something, believing something, wanting something. These are different attitudes toward the same proposition. This matters for modeling how agents think about the world and each other. Belief states represent possible situations an agent considers when making decisions. If you don't know whether it's raining, your belief state includes both possibilities. Decision-making under uncertainty requires reasoning about belief states rather than single certain states. Don't forget to grab those free practice questions from the link in the description. With the depth of knowledge you've gained today, plus practice from those questions, you'll be incredibly well prepared for your OA exam. Now let's tackle uncertainty and probabilistic reasoning, the final major section. Prior, or unconditional probability, is your belief in something without considering any other information. What's the probability it rains tomorrow before you check the forecast? That's prior probability, pure base rate. Conditional probability is the probability of something given specific conditions. What's the probability it rains tomorrow given that the forecast says cloudy? That given changes everything. Conditional probability is where the real reasoning power comes from. Joint probability distribution gives the probabilities of all value combinations. If you have two variables, weather and traffic, the joint distribution tells you the probability of every possible combination. Sunny and light traffic, rainy and heavy traffic, and so on for all pairs. Independence comes in two flavors. Marginal independence means two variables are independent, without conditioning on anything else. Coin flips are marginally independent. Conditional independence means two variables are independent, given a third variable. This simplifies calculations dramatically when it applies. Bayes' theorem is the centerpiece of probabilistic AI. It updates probabilities based on new evidence. You have a prior belief, you observe something new, and Bayes' rule tells you exactly how to revise your belief. Master this formula because it shows up everywhere on the exam. Bayesian inference is the application of Bayes' theorem to update hypothesis probabilities. You think there's a 30% chance of disease. Test comes back positive. Bayesian inference calculates the new probability, accounting for the test's accuracy, and the disease's base rate. The naive Bayes model assumes conditional independence of features given the class. This sounds technical, but it's practical. When classifying emails as spam, naive Bayes assumes that individual words are independent, given whether the email is spam. It's naive because that's not really true, but it works surprisingly well. Bayesian classifiers use Bayes' theorem for classification tasks. Given features of an unknown item, what's the probability it belongs to each category? Pick the most probable category. This approach works well when you have good probability estimates from training data. Open universe probability models handle situations where the set of possible outcomes can change. Standard probability assumes you know all possibilities. Open universe models don't. New entities can appear. This matters for real-world AI where you can't enumerate everything in advance. Poisson distribution models event occurrence in fixed intervals. How many customers arrive per hour? How many errors per 1,000 lines of code? When events happen randomly but at a consistent average rate, Poisson distribution describes the probabilities of different counts. Existence uncertainty means you're uncertain whether an entity even exists. Identity uncertainty means you don't know which entity you're observing because information is incomplete. A security camera might detect motion without knowing whether it's a person, an animal, or a shadow. Sybil attacks involve multiple fake identities manipulating systems. One person creates many accounts to game voting systems or reviews. AI systems need to handle identity uncertainty defensively because attackers exploit these gaps. If questions mention fake accounts or identity manipulation, think Sybil attacks. Let's pull everything together. You've now covered the 4 major areas tested on your D429 OA. AI Foundations gave you the vocabulary and philosophical context. Intelligent Agents taught you how AI perceives and acts. Knowledge Representation showed you how AI organizes and reasons with information. Probabilistic reasoning equipped you to handle uncertainty. The exam will test these concepts in various formats: definitions, scenario identification, calculations, and application questions. When you see a question, first identify which module it belongs to. That narrows your thinking immediately. Then look for keywords that point to specific concepts within that module. Here's my honest advice for exam day. Don't rush. Read each question carefully because wrong answers often contain terms from the correct concept area, just applied incorrectly. If you're unsure, eliminate obviously wrong answers first. Usually you can narrow down to 2 choices and from there, trust your preparation. You've built a solid foundation today. The concepts are in your head. Now the work is turning that passive knowledge into active recall, and that happens through practice. Go use those free questions. Work through them until you can answer confidently without hesitation. That's when you're ready. Good luck on your OA, you've got this.